Okay, good morning everyone. I'm going to record the lesson that we would have normally done in class today on Lewis theory of bonding, section 4.1. This is very much a review from what you've already done in grade 11, so this should be relatively straightforward for you to follow along with. So this is from your note package, I'm going to be following along here, so when you are doing this, make sure you have your notes in front of you and a periodic table. Okay, so first of all, the reason why we have the Lewis theory to begin with is because when we're looking at bonds and we're looking at how atoms come together to make molecules or compounds, you have to understand the electrons that are involved. So first of all, the reason why we have them come together is because the whole point is that we want to create a stable octet. So the term for that is we want to be isoelectronic to a noble gas. So meaning we want to have the same number of electrons, same structure of electrons as a noble gas. Electrons are the most stable when they are paired, we know this, and of course we have a stable octet is the end result. Now there are going to be exceptions to that rule. We saw a lot of those in grade 11, but we will review that again. So how they become a stable octet can either be done through transferring electrons, so if it's an ionic compound, we have a metal and a nonmetal, or we can share electrons, which means you have nonmetals only. So of course when you have a metal-nonmetal, you have an ionic bond. If you have the sharing of electrons, we have a covalent bond. So this is just a recap. So when we're drawing a Lewis structure, remember that we are showing electrons as dots, and we use a dashed line to represent the sharing of electrons. So first we're going to review ionic compounds. So sodium, right? So just to kind of review here, sodium is in group 1, has 1 valence electrons. Chlorine is in group 17, it has 7. So obviously it's a very simplified example. Sodium is a metal, so it is going to lose, and chlorine is the nonmetal, it's going to gain. So you have a transfer here. The end result, anytime you have an ion, you must have brackets and the charge in the top right-hand corner. So if it's a metal, you should show that it is now empty, right? So there's no electrons there in the outer shell. And then for chlorine, we should show that we have now all 8 because it's gained. And the charge is -1, right? So when you have ionic compounds, you keep adding however many atoms you need to ensure that everything is stabilized, brackets, and the charge. Now when you're doing covalent compounds, you're now showing the sharing of electrons. So notice, right, we have dashed lines to represent the sharing. Each dashed line represents 2 electrons, right? Any electrons that are not involved in sharing should be shown with your electrons. So you should have your dots there. So this is an example with water, right? So again, this is very simplified. So I guess in grade 10, you would have learned to draw it most likely in this way, right? So you have 1 electron being shared with another from one atom to another. And then, of course, the sharing, the circles are now represented by a dashed line. Okay, so obviously, even in grade 11, we never did it in this way because we have more complex structures than just H2O. Okay, so when we are drawing Lewis structures, just to remind yourself from the quantum mechanical model, when you're looking at an electron configuration or an energy level diagram, the Lewis structure is really only showing the highest energy S and P electrons. So remember, whenever we're drawing this, we're only looking at the valence electrons. So for example, if we were to be talking about, let's say, fluorine, right? So fluorine has 7 valence electrons. This doesn't mean these are all the electrons possible for fluorine, but these are just the highest energy S and P of fluorine atoms. And you'll see that in the next examples. Okay, so we're going to do magnesium. I know we had done this in class, but just to kind of recap, how do you know which ones are valence? So let's take a look here. So magnesium has 12 electrons, right? So we have a little template here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so in this case, the highest N number is 3, and the only electrons in the third energy level are the S. So when we're writing out the Lewis for magnesium, it's in group number 2, it has 2 valence electrons, right? That is being represented here. So we still have, of course, 1s2, s2p full, but we're only showing the valence electrons. And the reason why is because those are the ones involved in bonding. All right, so when we'll do one more, so nitrogen has 7 electrons, so we're going to do 1, 2, 3, 4, 5, 6, 7. So remember that you have to have 1 in each before you fill up, before you pair up the unpaired electrons. So the electrons that are valence, the highest energy level in this case is 2, and we have S and P 1, 2, 3, 4, 5. So that's why when we are drawing out the Lewis diagram for nitrogen, we have 5 valence electrons, right? Doesn't mean the 1s aren't there, it just means they're not represented when we're drawing our Lewis structure. Remember, that's a simplified version of the same thing. All right, so here you have this again, it's showing you essentially a nice little simplified chart. So it has the valence number, your Lewis symbol, what it would look like, and then the energy level corresponding to that. So we've done magnesium and nitrogen, so here's sulfur. So the highest energy level is 3. There are 6 of them. That's what's represented there, right? So high N number, and then the S and P in that N number. Okay, so when you're doing Lewis theory, there are going to be some that are going to break the octet rule. I've posted on D2L the PowerPoint from grade 11 that we had done that will review again how to draw Lewis structures, and it also reminds you which ones are breaking the octet rule. But essentially when we're drawing the Lewis molecule, the steps that you learn in grade 11 and that I'm going to review here today can be used for simple molecules and even more complex, especially when we're talking about polyatomic ions. So when we're talking about what this first point is talking about is in grade 10, that a whole idea about sharing electrons can explain only simple molecules but cannot explain more complex structures, which is why in grade 11 we don't talk about that anymore. We look at the more expanded version. So essentially the best way of me doing this is to go through some examples with you and go over the rules of this. There is, again, please watch that PowerPoint from the grade 11 review. So we're essentially just going to do some examples together. So here we have sulfate. So the first thing you want to do is you want to create your, what I call the electron bank. So essentially what we're going to do is we're going to add up all of the valence electrons, right? So add the valence electrons, and you also have to include the charge. So essentially I know I have 1 sulfur, 4 oxygens, and I have 2 extra electrons because of the -2 charge. So if this was +2, that means I would have 2 less electrons. And of course, if there's no charge, that means you just add up the electrons as normal. So my sulfur has 6 valence electrons, right? My oxygen has 6 also, but there are 4 of them total. So please excuse my writing. Obviously, I'm using a mouse, so it's not as smooth as it may normally be. So that's 24 coming from oxygen. So in total there, we have 30. So if this was a normal, no charge structure, it would be 30. But because it has a -2 charge, we're going to add in those extra 2 electrons. So we have 32 max that we have to work with in our structure. So this is our electron bank. So essentially that's this first step. Okay, so step number 2, I'm just going to draw it up here. What you would have to do then is decide what your central atom is. Okay, so majority of the time, the central atom is going to be the one that can make the most bonds. But in this case, sulfur and oxygen technically have the same number of valence. But if you look at the ratio that you have, it kind of will make sense, right? So if I have 4 oxygens and 1 sulfur, I really have 1 sulfur in the middle, and then I have 4 oxygens surrounding it. Okay, so here's my structure. You're then going to first start adding in electrons in the bond placement. Okay, so the first step is always to place the bond electrons because we have to connect them to each other. So remember that each one of these uses 2. So right now we've used 2, 4, 6, 8. So I've used a total of 8 electrons from my bank. Okay, so that means I'm left over with 24, right? So 32 minus 8, 24. So the next position that you're going to do, or place these electrons, is actually on the peripheral atom. So meaning the atom's on the outside. You never worry about the central atom until the very, very end. So each one of these requires another 6 electrons to have a stable octet, right? So 2, 4, 6, 8. And we'll do the same thing to all of them. So I've used up 8, 16, right? Oh, geez. Sorry, each one has 6 extra. I was like losing track. Sorry, ignore that for a second. So we have 6, 12, 18, 24. That makes more sense now. So we have finished the electrons in the bank. When you have finished your electrons, you're then going to do a check to make sure that every atom is stable. So right now, our oxygens are stable. Sulfur has 2, 4, 6, 8. So sulfur is also stable. So the last thing we need to do here, because this is an ion, is put brackets and the charge in the top right hand corner. Now if you put -2 or 2 negative, it's the same thing. Both are correct. All right, so that's that one. So we're going to do, the rest of this explanation is down here, but we've already covered that. Now keep in mind, when you make multiple bonds, that is only if, you can only create a multiple bond if it is an atom that has that ability. So typically we have carbon, nitrogen, oxygen, sulfur, phosphorus sometimes as well. So some atoms can, it depends on how many valence electrons it has. So for example, something like hydrogen cannot make a double bond. It only has 1 electron to share, right? Something like chlorine, right, has only 1 free available electron, so it cannot create a double bond. Okay, but you will have exceptions to this, especially when you do polyatomic ions, because, and if you review, please watch that grade 11 video, lone pairs of electrons can sometimes create coordinate covalent bonds, okay, and that will review that. That's why sometimes when you have polyatomic ions, you have some wacky structures. Okay, so here we have SF4. So again, we're going to do our electron bank. So our sulfur has 6 electrons. Our fluorines have, there's 4, and each one of them has 7. So in total, we are going to have 34 electrons. Okay, so looking at the ratio, right, we know sulfur's in the middle, and we're going to have our 4 fluorine around. And we're going to put our electron bonds in first. So 2, 4, 6, 8. We have used up 8. We have 26 left over. Okay, each fluorine needs another 6, so we'll give it its 6. And we now have used up, so we have 6 times 4, we've used up 24. So that means that we have 2 electrons left over. Okay, anytime you have extra electrons left over, they go on the central atom as a lone pair. So again, this looks kind of weird. Sulfur has here 2, 4, 6, 8, 10 electrons, but that's fine. Sulfur is one of the atoms that can break the octet rule. Okay, so there are a few. So sulfur, phosphorus, xenon are just a few that you'll come across. But if you remember that rule that if you have extra electrons, it goes on the central atom as a lone pair, you should get the correct structure every time.